And again, welcome to a new problem solving session. And we are still solving the problems related to tipping or toppling. And this time we got a problem about tipping of a hemisphere. And here is the problem statement. A uniform density hemisphere, that means mass density is uniform, that's fine, is placed onto a rough inclined plane of a small angle of elevation for time being, and the angle of elevation is slowly increased while fine. Then first part of the problem is asking to determine the angle of elevation of the slope when the hemisphere just slips on the verge of slipping on the incline. If the coefficient of static friction is 0.3, does this angle depend on whether the hemisphere is put onto the plane with its convex or plane part? I think it will depend. And after all, we are going to find it. And second part of the problem is, what is the angle between the slope and the plane part of the hemisphere at the moment when the sphere is on the verge of slipping, if it is placed on the slope with its convex part? The part B is when the sphere's convex part is put on the inclined plane. And part C must be asking when the hemisphere is put over the inclined plane by the side of its plane part. तो ये प्लेन सरफेस उसका रखना है या उसका कन्वेक्स साइड रखना है, इसके लिए क्रिटिकल एंगल्स निकालने हैं, इंक्लाइन को कितना उठाना पड़ेगा. So only part B and part C of this problem are relevant. Part A was just an information that coefficient of friction is 0.3 or something like. I guess there are many problems with us. We will face many difficulties while solving this problem. But let me solve this problem when its convex side is put over the inclined plane and remain in equilibrium. I have drawn a picture for it. This should be like this. This should be like this. I'm going to delete this thing. So this is the picture on the screen. In the first condition, this should be like this. And we all know that it can only, if it is on the verge of motion, on the verge of slipping, and still in equilibrium on the slope, if its center of mass, that is C in the figure, is located above the point P in contact with the slope, that means this CP line should be vertical. अब ये मूव करने के कंडीशन में आ गया, on the verge of motion it is. And we know one thing, what is this 3/8R? So according to the tabular data I was viewing earlier, the center of mass of a homogeneous hemisphere with a radius r is located at a distance 3/8r from its geometric center. That is, geometric center से उसका center of mass, it should be at a distance of 3/8r. and of course on its axis of symmetry, which is of course this line. This line is the axis of symmetry. So I guess we have enough information placed in the figure itself, and this line is vertical, and this is the normal line, normal to the normal to the incline, to the slope, and this is the line of symmetry of the hemisphere that must be perpendicular to this line, perpendicular to this line. So we have everything clear, so we can proceed now. If this angle is alpha, this is perpendicular to the slope. This line OP is perpendicular to the slope, and this line OC is perpendicular to this line, flat surface. So if this angle is phi, this angle is going to be phi, and since this is vertical and this is normal, so I guess this angle is 90 degree, this is 90 minus alpha, so this angle should be alpha, so we'll wait. I got the things. And I have a good triangle to utilize the sine formula. The triangle is OPC, and we can use the sine formula. Simply sine alpha upon 3 by 8r is equal to sine, this length is r, so this angle is sine pi minus alpha plus pi. So we can write here sine pi minus alpha plus pi, that is of course sine alpha plus pi divided by r. So this result gives us sine alpha upon sine alpha plus pi is equal to 3 by 8. And by putting tan alpha, the value of mu was given basically, and it is on the verge of slipping, so we can use here the limiting, we can find the limiting angle using the value of mu. Mu was given in this case 0.3. So basically this will be equal to tan alpha, and tan alpha equal to 0.3. So we can get the value of sine alpha, and we can get the value of phi. So we get something here. The value of phi we can get from this equation, and we can solve the result. We can find the required things. So this problem is solved. But if there is a condition, if the coefficient of static friction is larger than this 0.3, coefficient of friction, the value of coefficient of friction is larger than 0.3, and from this equation we can find that the maximum value of sine alpha can be equal to 3 by 8, because if we can vary the value of phi and alpha, still the maximum value of sine alpha can be 3 by 8. You can see this result from this equation. That means what? That means if sine alpha is greater than 3 by 8, then we can obviously find tan alpha corresponding to it. whatever value, 3 by 8 is the maximum value of sine alpha, which will not be in this case. The sine alpha, the value of sine alpha is 3 by 8. If sine alpha, when the value of sine alpha is 3 by 8, then there will be some corresponding value of tan alpha, and from that we can find the coefficient of friction as well. And in that case, this sine formula has no solution for phi. No phi is actually possible. In this case, no phi will be actually possible. And in that case, it will not be slipping, but hemisphere will overturn from the position initially put. That means if what I'm trying to say, if sine alpha is greater than 3 by 8, then for the corresponding value of mu that can be found from this value, the hemisphere can only overturn, it cannot slip. This is my take in this problem while solving this. If you understand this is better. Otherwise, you need to think and rethink. Ultimately, you will get the result. And second condition was simply when we put things like in this manner, this angle must be, I think, this angle must be, figure is not clear, this angle must be alpha, and the plane surface of the hemisphere is put on the slope, and slope is elevated slowly as the condition of the problem was required. And we have the case when it just started slipping, and we can find the value of alpha in this case. This is quite simple to find the value of actually you can easily directly find the value of tan alpha here. And in this case, tan alpha equals to perpendicular by base, that is r by 3 by 8r. Sorry, r by 3 upon 8r. So tan alpha will be here 8 by 3. So corresponding to tan alpha, you will get your mu, and this mu will be much greater than 0.3. I have calculated somewhere, got the data from Google, that if tan alpha equals 8 by 3, what will be the value of mu, and I got it around 2.67. So you will be needing much greater mu in that case. So alpha is different in both cases. When you put a hemisphere by its convex side on a slope, or by the plane surface, by putting the plane surface of the hemisphere on the slope, दोनों cases में alpha का value different, alpha is quite different. And in this case, mu is also different. So this mu 0.3 was provided in this problem only for this case. In this case, mu should be much greater than 0.3. So the value of mu and value of alpha both will be different in these two cases. Because to be on the verge of motion, we need to have friction should be equal to friction acting on it in this direction should be equal to simply mg sine alpha, and n should be in this direction, and friction limiting friction value is mu n. And then in that case you will get the value of mu equals tan alpha, and tan alpha is basically 8 by 3, so its corresponding value of mu is much greater 2.67. So it will be a different problem, and it is a worthy problem to be asked in IIT JEE, because it has too many challenges to think over. There are too many challenges to think over in this problem. I guess you will handle it properly, and you will give a thought over the solution or the problem itself. And if you think anything about it, you can share with me as well. Thank you.